Hello, everyone. Thank you for attending to our automation webinar today. I hope everyone is very well. My name is Mauricio, and I'm one of the automation specialists here in WEG Automation International Sales Department. And I'm going to be the host for today's event. First of all, please make sure that you follow us on our LinkedIn page and also into our YouTube channel, so you don't miss any updates about future webinars and automation news. There, you can also rewatch our past webinars to learn even more. For this webinar, as you can see, we are using the Microsoft Teams live event format. We have a Q&A chat available, so you can access it in your top right corner in your screen, where you can interact with us. So please, during the event, if you have any questions, let us know. Our automation team is in the backstage to promptly assist you with your questions. Today's webinar is Learn how you can apply industrial automation devices in harsh environments, and it has an estimated duration of 1 hour. Our speaker today is Altair Grat Jr. Altair is an electrical engineer with more than 10 years of experience in the sector. He is one of the automation specialists in our team, and nowadays he works more closely with WEG branches in Germany and Italy. With no further delay, I shall give the floor to Altair. Altair, the show is yours.
Thank you very much, Mauricio, for this introduction. Hello, everyone. My name is Altair. I hope everyone's safe, and welcome to today's webinar. Just like Mauricio said, the topic is learn how you can apply industrial automation devices in harsh environments. So if you have any doubt, you can use our chat in this streaming platform. So let's get started. So before I start, I would like to give a short agenda of today's webinar. So I will start by saying what the rating is. So when you use it, obviously in harsh environments, what are the main factors for product rating, for using the product in another way. Then I'm going to give several examples and applications of products according to these two main factors. So we go through variable speed drives, soft starters, circuit breakers, overload relays, contactors, and capacitors. And at the end, I'll give a wrap-up of this presentation and also let's say an expected FAQ, frequently asked questions that I believe you have, that we are going to have it at the end of this presentation. So first, a little bit of a definition. So what is the rating? Here I have two very short definitions. The first one is to reduce the nominal capability of an electrical or mechanical equipment due to its deterioration or insufficient performance. So let's think about a plastic material that because of temperature, its properties change, and then the insulation of this material also changes. Another definition could be, is the operation of a device at less than its rated maximum capability in order to prolong its life. So what are the most usual rating factors? So for the industrial electro-electronic devices, we consider that's temperature and altitude. So what is temperature? Basically, temperature is the measure of the average kinetic energy of the particles of a substance. Basically, it's what you measure with a thermometer in a comparable scale that can be degrees Celsius, degrees Fahrenheit, or Kelvin. Another concept that is really close to temperature is heat. So what is that? It's the thermal energy in transit. Basically, it's the energy that flows from a hot body to a cold one. Basically, it's the flow of energy between bodies. And how does it happen? How does the heat transfer? Basically, it can happen through three ways: conduction, which is through solid materials; convection, which is through the movement of air; and also through radiation, which is through electromagnetic waves. So here on the right, we have a heat exchanger, sorry. So basically here on the bottom, we can see a hot fluid represented by the red color going through this heat exchanger. And at the end, the temperature goes down. Why? Because there is this air flowing through these tubes that will absorb the heat from this fluid. Obviously, this airflow has to have a lower temperature, so the heat can be transferred from the hot body, in this case, this fluid, to the cold body, the airflow. So what are the problems and risks that you can have by applying a product in temperature above its nominal? So properties can be altered. So color can change, consistency can change. You can also have deformation of the materials, and then it can lead to equipment breakdown and maybe even constant replacement, which will affect your productivity in your process. So you can not only lose money by changing components in a machine, but also because you cannot make your production constant. And at the end, depending on the breakdown you have, on the problem you can have a permanent equipment damage. So then you have to change the whole machine. Here, at the bottom of this slide, we can see two pictures. Basically, it's the same picture, but on the left we have, let's say, a normal one, and on the right we have a thermal photograph. So here we can see which components are hotter and which ones are, let's say, less hot. So here behind this barrier that we cannot even see here, there's two components which temperature reaches 57 up to 58 degrees Celsius. So these are the hot spots in this panel. And on the top of these VFDs, of these frequency variable drives, variable frequency drives, the temperature is also very high. And this picture was taken with the panel doors open. So can you imagine how hot can be this panel once the doors are closed? Another concept I can give you here, another example, is for electrical motors. So by using this motor at a higher temperature, here, for example, 10 degrees Celsius above the thermoclass limit of the motor insulation, you can reduce the lifespan of this motor by half. So imagine the impact that you would have in your industry, in your process plant, by having a reduced lifetime of all your motors, and especially by half. So where can we find these, let's say, high temperature places? So there are a lot of places in the globe where temperatures can be very, very high, like in arid regions or in tropical regions. And in those regions, we can find industrial installations where the internal temperature of the installation will be even higher. And imagine a equipment inside a panel inside this installation in a very hot area. So you have this accumulative effect. But even if the ambient temperature is not high, your application, your industry may create a lot of heat. So let's take here this example on the right side of this slide. Here we have a foundry, a blast furnace. So can you imagine how much heat this equipment can create to the environment? So then your equipment probably is going to be close to it, so it's going to be affected by this temperature. Now we are going to move to the second factor of product derating. Now it's altitude. So what is that? Basically, altitude is the increase of vertical elevation compared to the sea level. And as we go up in altitude, there is one effect, which is the decrease in the air of the environment. So here this picture is depicting a lot of particles, these blue particles here, showing the density of air you have here, but as you go up, you have less and less and less. So let's give another explanation about it. So as the altitude goes up, the pressure goes down and the gas concentration goes down, meaning that the heat exchange will go down as well. Why? So let's look at this example here. We have an equipment that's operating at the sea level. It's here at the base of the mountain. when it's operating, it generates heat and the temperature goes down. The temperature goes up in it. So these red particles here represent how hot this equipment is, so how much heat it's being generated. But as time goes by, these blue particles that are representing the air surrounding the equipment will absorb part of this heat, and throughout time, most of the air around the equipment will absorb most of the equipment's, let's say, hotness, most of the heat, meaning that the equipment temperature will go down, the equipment will cool off. But if the same equipment to a higher altitude, so here at the peak of this mountain, that's not going to happen because the density, the concentration of gas here in the peak of this mountain is not as big as you have here at the sea level, meaning you have less blue particles to absorb this heat. And even after some time, the air will absorb part of it, but not enough because you don't have enough air to absorb this heat, meaning that the equipment will remain hot. Here we have another effect of the altitude that can affect your device, your equipment. As we go up in altitude, we know that pressure goes down, gas concentration goes down, but also the dielectric strength goes down according to the Paschen's law. So how does it happen? Let's take here an equipment, once again, at the sea level with this pressure, 1 atm. Let's say that's a contactor. So here we have two energized contacts, and you have an insulating material between them. So the operation here is completely safe. But because we are going up with the same equipment, the dielectric strength goes down, meaning that you need less voltage to break it. So the breakdown voltage of the air here in high altitudes is much lower, meaning that a arc could happen. And then obviously in this case it would be a short circuit between phases, which can be really dangerous. So what are the problems and risks related to high altitude? So what can it cause? So it can decrease the heat exchange between equipment and environment, which is bad. It can lead to all problems and risks related to temperature, like failure and breakdown that I have explained a few slides ago. And also it can lead to short circuit in the components, leading to really dangerous and harmful incidents like fire or something else. So where can we find these high altitude applications? Obviously in high mountains, but do we really have these applications that high? So here we have some cases in which mines, they operate extracting minerals in the Andes up to 5,000 meters. So there are mines that are extracting copper, silver, gold, lead, iron. So these applications do really exist. And here on the right, on the top right of the slide, you can see two pictures of two panels. These two panels are actual products from WEG being applied in high altitudes. So now that we have learned these two main factors that can affect the performance of an electrical equipment, what can we do about it? How do we solve it? Well, we have to apply some derating factors when needed. So the idea is to keep the life of the product operating in a lower capacity. But before we start, I would like to say 3 points. First, all electro-electronic devices are subjected to these derating factors because the physics is there for everyone. If you take any product and you take it to the peak of a mountain, 3,000 meters high, they will be somehow affected. The temperature is the same. But in this presentation, and because this is a WEG webinar, I'm going to give examples with WEG products, obviously. Another topic I want to say is that the motors, most of the loads that I'm going to use as applications here, I'm not going to derate it. I will already consider that it was already derated, or motors have a advantage compared to other electronic products or components. Electric motors, they can have their frames increased, or you can use bigger frames for the same motor. This way you can improve the heat dissipation of it. So they have a plus compared to other components. And what are the source of these factors? So from where did I take them? Basically, these factors can be obtained from tests in laboratories, like in climate chambers, where you can control temperature, humidity, and on. You can get it from softwares like ANSYS. Also, some standards can determine the maximum operational conditions of this product. Let's go to the first product. The first one is a variable frequency drive that I will simply say here drive. So the main effect of the derating factors are on the rated current. So both altitude and temperature affect the rated current of this product. So if we take like technical data from this specific CFW11 up to 88 amps and in this IP degree of protection, we can learn that we can use up to 1000 meters without any derating, and we can use from -10 to +50 degrees Celsius normally. However, if you want, or if you have to exceed these limits because your application requires, we have these two tables here for each factor. First one is altitude. As we go up in altitude, we have to use these factors here. So if you have, for example, a 10 amp VFD and you have to apply that 4,000 meters, you have to multiply by 0.7, meaning that the CFW11 can only deliver 7 amps. Another way of saying that is, instead of multiplying by a factor, is decreasing by a percentage. I'm going to give some examples about it later. And here on the right, we have a similar table, but for temperature. Another way of saying that is that for every meter you go up, in this case here, for every 100 meters, you have a derating of 1% in rated current. The same happens with temperature, however, it's 2% per degree Celsius. So let's make an example to clarify it. So let's say that you have a VFD and you have to size it for a 43 amp motor up to, applied at 4,000 meters of altitude. What do you do? First, you have to calculate this gap altitude between the application altitude and the maximum altitude you can apply this VFD without any derating. In this case, it's 3,000 meters. Then use this value and multiply by the factor. We have learned that for every 100 meters you go up in altitude, you decrease 1%, meaning the total derating is 30%. So let's select, for example, a 70 amp VFD. You take the nominal current of 70 amps and then you decrease 30%. The final value is 49 amps, which is higher than the motor's current. So you can use it. Let's make another example, but now with the temperature. Let's use this VFD at a higher temperature than the nominal one. The motor is the same. What do we have to do? Once again, we have to find this temperature gap between the application temperature and the nominal temperature of the VFD. So this gap is 5 degrees Celsius. Then you multiply by what? By the 2% per degree Celsius you go above the limit. So the total derating is 10%. So let's select here a 58 amp VFD, and then we decrease this 10% of the derating. So now let's say the max current that this VFD can deliver at this condition, 55 degrees Celsius, is 52, which is higher than 43. So okay, you can use it. Last example for VFDs. You might question yourself, what about an application where we have both derating factors, the altitude and the environment, so 4,000 meters and 55 degrees Celsius environment? So let's see. In the previous examples, we have learned that the altitude derating is 30%, the temperature derating was 10%, so the total derating would be 40%, or the factor would be 0.6 if you sum them. However, that's not the most cost-efficient way to calculate the derating factor, because actually you can multiply them instead of making the sum. Why? Because factors, they can compensate each other. So instead of making the sum, you multiply, and then the factor, instead of being 40%, is going to be 37%. Let's take a look at this table here. This table has two big areas, the dark gray area here on top and left, and the other one here on the bottom and right. This table says the following, that on the dark gray area, the compensation of one factor is so big compared to the other one that no derating is needed, so the factor is always 1. This other area here shows the factors multiply themselves. So it's a factor of 4,500 meters, for example, with a 55. So that's going to be the multiplication between them. Let's go back to the example and see what happens. So if we take a 88 amp VFD and decrease the derating factor, the total derating factor, using the sum, you find that this VFD can deliver 53 amps, which is higher than 43. There is no problem, it will operate it correctly. However, maybe it's too much for this application. By using the table I have just shown you, we can use a new factor which will allow us to use another VFD, a 70 amp VFD. So instead of using a 88 one, use a 71, because the new rated current of this VFD in this specific application is 44 amps, which is more than 43. So with this solution, we are more cost efficient, because as engineers, we cannot provide only the suitable technical solution, but also the most cost efficient one, because we know very well that money is a limited resource. So yes, you can use this one. And just by using a smaller VFD, you can have a lot of savings, especially in big plants. So now we are going to move to another product, the soft starter. Once again, the derating factors, altitude and temperature, they do affect the rated current of this product. If you take the technical data of this soft starter 900 from WEG, we know that we learned that up to 1000 meters, there is no derating here, as we can see. Up to 412 amps, this product can be used up to 55 degrees Celsius without derating. And from 480 amps and up, you can use up to 40 degrees Celsius. And above that, you can apply some derating. We're going to talk about it in a moment. So for altitude, we have this table here with also these derating factors. It's very straightforward. However, when temperature varies, there is no simple table where you can get a factor. You really have to learn how this soft starter is used. I'll give an example right now. So you have to learn about the application, the utilization category of this soft starter according to this IEC standard, which is IEC standard for low voltage components, and especially here soft starters, and the duty cycle of it. Why? Because the application of soft starters can vary a lot. Here I'm going to show you an example of how WEG describes the application of this soft starter, of a soft starter, very briefly. So this code here is a way to summarize several data. So the first part here, we know that's the full load current of the soft starter. The second part, AC53A, means the utilization category, and in this case is a soft starter without integrated bypass. 4 means the start current, 30 is the start time, 50 is the duty cycle, means 50% on, 50% off, and the last number here means the number of starts. But we could have another application in which a 130 amp soft starter is being applied with an integrated bypass, the start current is now 3, the start time is 30, and the normal condition time is 330, meaning that you're going to have 10 starts per hour. So here on the right, we can see a picture of a soft starter with integrated bypass. So during the start, all the current goes through the semiconductor switching devices, but then after the start, this switch here is it's on, so all the current is carried here. Sorry. That means that by doing so, the lifespan of these semiconductor switching devices is extended because you are not using it all the time. And just you to know, all models of SoftStarter 900 have bypass on it. So now that we have learned that we have to be very specific with the application of the SoftStarter, now we can use a table to derate it. So this table here considers a SoftStarter being connected with 3 cables at 55 degrees Celsius and 5 starts per hour. So here we have some models of SoftStarter 900, and as we go right here in this table, we see that the start current goes up 2.5, 3, 3.5, 4, and on and on and on, meaning that as we go right here, the derating factor is higher. So now that we have learned how to select the current according to the application, how do I make the, let's say, full derating of a soft starter considering temperature and altitude? So first, use this sort of table that's available in our technical materials, so in the user manual of this product, and then you apply the altitude derating factor. In case you have other sort of connections, for example, inside the delta, other temperatures, or with other number of starts per hour, just check our documentation as well. We have tables for several applications. Okay, let's give an example about it. So we have this soft starter, and we have to apply it in a motor of 523 amps, and the environment has a temperature of 55 degrees Celsius and the altitude is 2000. It's given in the information that the start current is 3.5 times the full load current of the soft starter. The start time is 10 seconds, and you have 5 starts, up to 5 starts per hour. And it's also a variable torque load. If you take this information, we can create that coding that I talked to you about before. And by using this table, let's say we take a 670 amp soft starter and we cross with this information here, with this application, which is quite close to what we have here, this soft starter can deliver up to 590 amps. Then we apply the altitude derating factor. So we make the difference between the application altitude and the maximum altitude of the soft starter without derating, which is 1000 meters. Then you multiply by the derating factor, which is 1% for every 100 meters. In other words, 10%. So finally, the 670 amp soft starter at sea level can deliver in this application, in this condition, 590 amps minus 10% of the altitude, meaning that the current that's delivered by this soft starter is 531, which is more than 523, the current of the motor. So yes, you can use it. So now let's move to the molded case circuit breakers. Once again, the same factors we have here, altitude and temperature. Both of them affect the rated current, but the altitude affects the voltage or whatever is related to voltage to this circuit breaker. Because as I told you before, the breakdown voltage of the air in altitude, in high altitudes, is lower, meaning that some factors, some technical characteristics of this product is going to be affected. I'm going to say more about it shortly. So let's take some technical information from this circuit breaker. It's the DWB160. So the product catalog says that up to 2000 meters, there is no derating, and up to 45 degrees Celsius also, there is no derating. In case you exceed these values, as you go up in altitude, there is a derating factor for current, like shown here, and another one for voltage. And then for temperature, in 45 degrees Celsius, the factor obviously is 1. If you go up in temperature, you have a derating factor decreasing the total value of this circuit breaker. However, in lower temperatures, you can even have like a boost in the rated current. But remember, you always have to consider the ambient temperature to make this sort of sizing. For more tables in terms of temperatures, you can check the product catalog. So let's make an example to see what happens with the current and voltage. So here, let's see if this model case breaker DWB 160 can be used in these conditions, 60 degrees Celsius and 3,600 meters. First, we use the derating factor of this breaker. So here we have the rated current, 160. You multiply by the factor of current for altitude, 0.93. Then we use the other table for the temperature, 0.91. Finally, you have the current of 135. Let's give an example about voltage. So the insulation voltage, the original, it's 800 volts. However, when you apply the derating factor for voltage of 0.78, according to the table, it goes down to 604 volts, meaning that if for some reason you have a higher voltage than that in this product, an arc could happen between phases, for example. Another product that's a circuit breaker as well is the motor protective circuit breaker. Once again, just like the MCCB, the motor case circuit breaker, the same factors apply, altitude and temperature. So this is technical information of this product, the MPW18. And in this case, it can go up to 80. It's valid for all this range. What is different here is that this product has a temperature compensation device inside of it, meaning that from -20 to +60, you don't have to care about derating. But when you go up from 60 to 70, then you have to apply derating. Here we have some tables showing us the factors in case we exceed these values from 2000 to 5000 meters, current, voltage, and then the ambient temperature derating factor. So here the maximum operating temperature of this product is 70 degrees Celsius. Another product that we can talk about is the overload relay, the thermal overload relay. Once again, the same factors apply to rated current, altitude applied to voltage, so the insulation voltage is affected by altitude. Here, the technical data says that we can use up to 2000 meters without derating. The operating temperature is from -20 up to +80 degrees Celsius. That's due to the plastic materials we are using on it. And this device, just like the motor protective circuit breaker, also has a compensation mechanism that up to 60 degrees Celsius, no sort of compensation in temperature has to be done. Once again, more tables explaining, giving us factors to reduce the rated current or voltage of this component in case we use in higher altitudes or here in higher temperatures. But I'd like to explain something that usually creates a lot of confusion in people's mind. So this is an adjustable device. So you can set the current to be protected through an adjustable device. How do I adjust it, considering that now I have a derating in the current? So the dial here shows that up to 60 degrees Celsius, because there is no derating at this temperature, you can protect a three-phase motor from 15 to 23 amps. However, if you take the same product to a place where the temperature goes up to 70 degrees Celsius, even though it's showing 23 and 15 amps, actually this overload will protect from 12.2 to 18.3 amps. The same happens to other adjustable devices like the MPW I have just shown you. So now I'm going to talk about contactors. Once again, altitude and temperature, they affect the rated current and voltage of this product. Here, the line CWB from 9 to 125 that you can see here in the picture, it can be applied, it can be used up to 3,000 meters without any derating. And then you question yourself, well, how is that possible? Because of high technology of this product, the materials that we are applying and the robustness of it. And the non-derating range of temperature, let's call it this, it's from minus 25 up to plus 55 degrees Celsius. In case you exceed it, we know that we have tables showing that to us. So up to 40,000, 5,000 meters, and we have these factors here. And here on the right, we have a table giving us the maximum current that a contactor can deliver in different temperatures. Okay, enough tables, and let's make an example. So let's check if a direct online motor starter comprised of a motor protective circuit breaker, MPW40, maximum current of 40 amps, and a contactor of CWB38, so normally 38 amps, assembled inside of an electrical panel is correctly sized to start safely a motor of 38 amps. Here the temperature, the ambient temperature is given, is 55 degrees Celsius, but this temperature, it's outside the panel. So what would be the temperature inside the panel? Well, you have to measure. In this case here, we are considering that 60 degrees Celsius. This temperature varies, and it depends on the number of components you have inside of it, on how much heat it dissipates, so each case is different. So let's first take a look at the MPW40. Up to 60 degrees Celsius, there is no derating, so you can use this MPW40. Then let's take the CWB38. So up to 55 degrees Celsius, it can deliver 38 amps. However, in 60 degrees, using the 65 degree data that we have available, it can only deliver 30 amps. So we cannot use this one. Let's move to the CWB50. So up to 55 degrees Celsius, it can deliver 50 amps, and up to 60, or actually 65, but as the application is below this limit, it can deliver 40 amps. So yes, you can use this contactor. So the new starter will look like this. The MPW40, it's okay to be used, but the CWB38 has to be replaced by the CWB50. Now, the last product I'm going to talk about is the capacitor for power factor correction. So the first derating factor is temperature. So it definitely affects the maximum ambient temperature that the capacitor can support. Every capacitor for this application, according to the standard, this one, the IC 60831, says that you have to classify your capacitor according to this code. First, we have a number that represents the minimum ambient temperature that this product here, in this case, UCWT, a three-phase power capacitor, can withstand, minus 25 degrees Celsius. And the second part, the ladder, represents the maximum ambient temperature and max average temperature it can withstand during a period. To be clear, I'll show you this table that you can find in this IC standard. So as we go up from A to D, the maximum temperature also goes up, not only the, let's say, instantaneous maximum temperature, but also the max average in these periods of 1 day and 1 year, meaning that the higher you go here, the more robust your product is. And that's the case of WEG capacitors. The UCWT capacitor is this category here, this classification, minus 25D, meaning that you can go from minus 25 up to plus 55 degrees Celsius. But what happens if the temperature, or if you have to apply this product in a higher temperature than this one? You have to guarantee that the temperature cannot go beyond this limit, either by natural ventilation or through forced ventilation. The other factor is altitude. And once again, that affects the maximum ambient temperature of this capacitor. So as we go up in altitude with this product, the maximum temperature surrounding the capacitor has to decrease. And once again, if you have a higher temperature than expected, you have to use forced ventilation. But there is a positive effect as you go up in altitude, is that as you go up, temperatures, the ambient air temperature goes down, making easier your job of reducing the temperature around this capacitor. So now we are closing this webinar, but first I would like to give some say a wrap up of this presentation. So what can you take from it? So you have learned that temperature and altitude are very important factors when you are applying these devices, electronic devices. You have to understand very well your application and environment, because these harsh environments, these harsh applications can definitely alter the functioning of the product. You always have to check the industrial automation devices technical materials, because just like I said, for every different product I talked about here, tables change, the derating factors change. Finally, you can always count on WEG for support to apply products, these automation devices in harsh environments or even in normal ones. So if WEG products can be applied in harsh environments, so you can imagine that our performance in normal conditions is going to be really good. So now here I have separated some, let's say, expected frequently asked questions that probably you have after this webinar. The first one is, okay, Altar, you said that we have derating factors for temperature, but can't we use forced ventilation in all of them? Yes, of course you can. However, there is a cost for it, and also your panel can probably get bigger because of it. So can your application fit this new panel, for example? Or also there is the cost versus benefit. So what is better in your case, in your application, to use a forced ventilation panel with normal condition components, or would it be, let's say, more cost efficient to use regular panel but with components being underrated? So the answer, it's up to you. The next question you might have is, what about mineshaft application? So should I size my components according to the surface level or underground level? So let's go back to the Andes, for example. We are there in Colombia or Peru or somewhere there, in somewhere like 3,000 meters high. But then your mine goes down 1,000 meters. So should I consider 3,000 meters or 2,000 meters? So in our experience, customers tend to rate all the components according to the surface. This way, they standardize all the site data. So all the spares, they're all the same. It doesn't matter if you're going to use it on the surface or underground. A big issue when you are in a mine shaft application is the ventilation, because if you're down 1 kilometer in the middle of the ground, how do you get rid of ventilation? So probably you have to use forced ventilation through some sort of closed loop air conditioning system or something like this, but it depends on your application. Also, another factor, just like altitude and temperature, could be humidity. And I haven't said anything about it during the presentation. Well, most of products, they can withstand a wide range of humidity levels without any sort of problem, as long as they are non-condensating. So if they are non-condensating, we can see here some cases that our VFDs and soft starters can be used from 5 to up to even 95% of humidity in there, and nothing happens. MCCBs, the same, can go up to 95%. But if this moisture, if this humidity condensates, and then you have practically like water in your component, so that can be very, very dangerous. So How do I solve it? So the idea is to use space heaters. So you should first use space heaters, make sure there is no or at least low humidity in your panel, and then you can use it. And that can lead to another harsh environment, which is the low temperature one. I haven't said much about low temperature, but that can be solved once again by using space heaters. So before using your application, you have to warm up your panel so your components, your devices can operate correctly. And in conjunction of humidity and low temperature, not only water you can find your panels, but even ice. So you have to make sure that you first melt down the ice and then you start your panel. So this is it for today. Thank you very much for your time here. I hope you have learned new concepts. You have new knowledge about application of these products, automation products in harsh environments. If you have any question, our chat is still open for it. So you can write down there and our team of sales engineers are going to answer them. Uh, I hope you have a nice day, stay safe and healthy, and I see you in our next webinar that's going to happen next month. Thank you very much and bye.